Hey, what's up? It's your old pal, Mr. Cook, and we are working on the Unit 7 group work. All right, so this is going to require you to, have knowledge of your unit circle, the identities, and also the half angle, double angle, and sum and difference formulas. So if you don't have those memorized, then, at least have them next to you so you can reference those whenever I, call back to them. Okay, anyways, let's see here. Let's simplify the given expressions. Make sure to state all fundamental identities used. So simplifying is pretty easy. We did a video on a whole bunch of these, and I'm sure that these will probably be very similar to those. One method that we use pretty regularly on these problems is converting from sine to, converting to sine and sines and cosines, using the reciprocal identities, quotient identities, and so on. So, you can probably do those for the vast majority of these problems where you have to verify or simplify. That's, in fact, what I'm probably going to do on this first one. I'm going to turn that cosecant, use a reciprocal identity there, and turn that into 1 over sine of x. And then tangent, I'm going to use a quotient identity there. Same thing with cotangent, quotient identity. Tangent turns into sine of x over cosine of x. And then cotangent turns into cosine of x over sine of x. Now, whenever you have two fractions that are adding, if it's verifying or simplifying, you want to add the two fractions together and make them into one fraction. It's just like an easy step to do. And we're also going to do that in number 2 with one method for solving. Actually, no, I'll probably do the factoring one on that one. But okay, so we want to find the common denominator here. So like I've got a cosine here and a sine here, so I'm going to multiply this one's denominator over here. So multiplying the sine in the top, sine in the bottom. And I'm going to take this one's denominator, multiply it over here, cosine in the top, cosine in the bottom. So now our fraction in the denominator looks like this. Sine times sine, which is sine squared, and then over sine cosine. So sine of x, cosine x. And then I have cosine times cosine, which is cosine squared. And they're adding together in the middle, and they have the same denominator, so I can just leave it like that. And then this should look familiar because sine squared plus cosine squared, that's an identity. So this turns into 1 over sine of x over 1, so that's a Pythagorean identity, turns into 1 over sine of x cosine of x. Then when you divide by a fraction, it's the same as multiplying by the reciprocal of that fraction. So that's what I'm going to do next. Just turn that into 1 over sine of x times, and then the reciprocal of this would be sine of x cosine of x over 1. And then it's a fraction times a fraction, so I just multiply straight across, and I get 1 times sine of x cosine of x. That's sine x cosine x over sine of x times 1, which is sine of x. And then you'll notice that the sine of x's will cancel out, leaving us with our simplified expression, which is just cosine of x. All right, the second one, you can do the sines and cosines thing. That'll work. You'll get some fractions. It'll end up working out. But I'm going to take this a different route. I'm just going to use a lot of identities. And in particular, the Pythagorean identities, the ones with secant squared and then also the ones with cosecant squared in them. So just, take a look at those while I'm working on them, and you'll start to see the Pythagorean identities. And, of course, I'll circle them when I use them as well. Okay, so first thing I would notice is that I have a secant squared for this term, and I also have another secant squared on this term. So what I'm going to do is factor out that secant squared. So I get secant squared of x on the outside, and then what I'm left over with on this one is cosecant squared of x minus 1. Okay, and then for this, the remainder of this stuff, minus cosecant squared of x plus 1, that actually looks almost identical to this, the different signs and everything. It's just that they're opposite signs. So if I were to divide out a negative 1 from both of those, so divide out a negative from both of these terms, I'd end up with the following. I'd get cosecant squared of x minus 1. And you can, check to verify that. What I've done right now is just factor out the negative, but if I were to distribute it back in, negative of cosecant squared is negative cosecant squared. Negative of negative 1 is a positive 1. So this is the same thing as this. I just, factor out the negative. I can do that if I want. So another thing that you might have noticed is that cosecant squared of x minus 1 is an identity. This is cotangent squared. So this is a Pythagorean identity, and so is this. These are both Pythagorean identities. They're the same one. They both give you cotangent squared of x. So that's what that's going to turn into. So I've got secant squared of x times cotangent squared of x minus cotangent squared of x. And, basically the same thing that I did in the first step. I'm going to do the same thing here. I've got these two terms. They both have a cotangent squared, so I'm going to factor out that cotangent squared. So what I get is cotangent squared of x, and then times parentheses secant squared of x minus 1. And then you might have noticed that this is an identity. This turns into tangent squared, so it's a Pythagorean identity again. And we get cotangent squared of x times the tangent squared of x. Well, as you know, these are reciprocals of each other, so I'm going to use the reciprocal identity on this one. I could have used the other one also if I wanted to, but reciprocal identity of cotangent squared is 1 over tangent squared times tangent squared. And then when I multiply those together, I get tangent squared of x over tangent squared of x, which of course is just 1. So 1 is my answer overall. And even if you, converted to sines and cosines, you still would have ended up with 1 eventually. So you could have practiced it that way as well. But that's it for number 2. Now let's move on to number 3. So number 3, let's see, this is verify the identities. So you know what, let's just go ahead and do the same thing that we did before, do the sines and cosines stuff. Because I guess one thing that I noticed with the partner quizzes and just working with kids individually is that they can always go to that step of, converting to sines and cosines. So if that's the thing that you like to do it. Stick with those methods. It'll even work for this one, okay? It's just a different one. Maybe if I have some time, I'll go over that one as well. But let's practice this one. Let's convert to sines and cosines. So secant, that's a reciprocal identity. That'll turn into 1 over cosine of x, and then minus cosine of x, over, and then tangent, I can turn that using a quotient identity into sine of x over cosine of x. All right, so you could go about this a couple different ways from here to get to sine of x. You could, combine these two together by using a common denominator and all that stuff. But I'm just going to show you a step that you can do here to, fast forward through it a little bit. What I'm going to do is, since I'm dividing this whole expression by this fraction, I'm going to do the keep, change, flip kind of thing and, keep the top part. 1 over cosine of x minus cosine of x. And whenever I divide by a fraction, it's the same as multiplying by its reciprocal, which would be cosine of x over sine of x. Then what I would do is I'd distribute these into here. So cosine of x over sine of x times 1 over cosine of x. So that would look like this so far. Minus, and then it'd be cosine of x times cosine of x over sine of x. All right, so these are equivalent so far. And next, what I would do is just multiply this stuff together. So I'd get cosine of x over cosine of x sine of x minus, and then cosine times cosine is cosine squared over sine of x. And then the cosines here cancel out, leaving me with just 1 over sine of x minus cosine squared of x over sine of x. And since these have the same denominator, I'm going to combine them together, and that gives me 1 minus cosine squared of x in the numerator, and then sine of x in the denominator. And as you can see, this is going to turn into a Pythagorean identity. This is a Pythagorean identity, and it'll turn into sine squared of x over sine of x. And then finally, if I have sine squared of x over sine of x, one of the signs will divide out from the top and the bottom, and we end up with our our result that we wanted, sine of x. All right, so that's number 3, just using sines and cosines, no big deal. Next, number 4. So number 4, we, this is an identity thing, obviously, but this is just one of the formulas that we've been using. This is the sum and difference formulas. So this is what we call the sine sum formula, and then this is going to be cosine of two angles subtracting. So this is going to be the cosine summation. Actually, I'm sorry, that's not sum, that's a difference. So the cosine difference formula that we have. And I'll show you what those look like. So the sine of an angle plus an angle looks like this. This is the formula for it. Sine of u plus v is equal to, and then it'd be the sine of the first angle times the cosine of the second angle, and then plus the cosine of the first angle times the sine of the second angle. So we use this formula with this setup over here, and we would get the following. So theta is equal to u, and pi is equal to v, so we just plug them on in there, and we get the following. Sine of theta times cosine of pi plus cosine of theta times sine of pi. And the reason that this is really neat is because coincidentally, or just on purpose, we're using unit circle values so that we can find their values, their exact values, and plug them in a little bit. But first we got to do this thing, okay? So we got to do the cosine difference formula, and that one looks like this. The cosine of u minus v is equal to the cosine of u times the cosine of v plus the sine of u times the sine of v. Okay, so if I use theta for u and pi halves for v, I get the following. So now I do this equation. So it's going to be the cosine of theta times the cosine of pi over 2 plus the sine of theta times the sine of pi over 2. So get your unit circle ready. Let's figure out what these are. So the cosine of pi, I can find that. The sine of pi, I can find that. The cosine of pi over 2 and the sine of pi over 2. So look on your unit circle, find those values. You should get the following. Sine of theta and then cosine of theta, that's going to be -1 plus cosine of theta times the sine of pi. Sine of pi is 0 plus cosine of theta times the cosine of pi over 2. So the cosine of pi over 2 is 0 plus sine of theta times the sine of pi over 2. The sine of pi over 2 is 1. So if we multiply those values together, sine times -1 is negative sine of theta. And then cosine of theta times 0 is just 0, because anything times 0 is 0. Same thing with this one. So those both cancel out, basically, or add to 0. And then sine times 1 is just sine, so we just have negative sine of theta plus sine of theta. And, once we just add those two together, we end up with 0. And that's exactly what we're trying to get in the first place. So that's number 4, using the sum and difference formulas. Make sure that you're familiar with those and you know when to use them. All right, so number 5 and number 6, these are just solving expressions using, finding the solutions and leaving them as radians. So again, these are going to require you to use the unit circle. So make sure you know how to read your unit circle. Practice it if you don't know, and if you do know, then it's going to be pretty easy. Okay, so let's solve. In either of these cases, what our goal is to do is to get like one of the trigonometric functions, like sine or whatever, equal to some number. Okay, so we want to isolate the trigonometric functions. So to get the trigonometric function here, cosecant all by itself, what I'm going to do is add 4 to both sides, so I get 3 cosecant squared of x equals 4. I divide by 3, so cosecant squared of x is equal to 4/3. Then I take the square root of both sides. Now, you might remember that when you take the square root of a squared variable like this, like x squared equals 1, if I take the square root of both sides, then x is not just equal to 1, it's equal to positive and -1, because the negative solution also works in there because of the symmetry that's involved there. So the same thing works whenever you take the square root of a squared variable. You need to do the same thing with the cosecant. When you take this cosecant, the square root of cosecant squared, then you also you need to take out the plus or minus that's in front of there. All right, so now let's evaluate this square root of 4/3. So square root of 4/3, the fraction, is the same thing as the square root of 4 over the square root of 3, because I can split apart the fraction like that. Square root of 4 is 2, and the square root of 3 is the square root of 3. And I'm going to leave it like that, because I'm actually not going to keep it as cosecant for long, because cosecant isn't on my unit circle. Cosecant's not like on my calculator explicitly. To find these angles, x, which is what we're trying to do, solve for those angles, it's equivalent to just find the sine of those angles. As long as you take the number that you associated with your cosecant and just take its reciprocal. So we're just going to have positive and negative and then the reciprocal of this, which would be square root of 3/2. And the reason that I'm taking the reciprocal here is because I want sine, which is the reciprocal of cosecant. All right, so now what this is asking me to do is find all of the angles x that have a sine of square root of 3 over 2. So that means that we're looking for the angles that on our unit circle, because this is a unit circle number, square root of 3 over 2, all the angles that have a sine that's the square root of 3 over 2. So if you look on your unit circle, look at the y values, the sine values, and find which ones have positive square root of 3 over 2. So if you look on your unit circle, those ones should be pi over 3, and then also 2 pi over 3. And then also, you'd want to find the angles that have a sign that's negative square root of 3 over 2, because it's plus or minus. So the angles that have a sign of negative square root of 3 over 2 on your unit circle are 4 pi over 3 and 5 pi over 3. So all 4 of these answers are solutions to this initial equation up here, this trigonometric equation. So if I were to take pi thirds and plug it in, I'd end up with 0. If I plug in 2 pi thirds, 0, and so on, okay? And those are our answers in radians, and I know to use radians because this tells me right over here, the domain. Okay, so 4 solutions for that, and you need all 4 to be correct on a problem like this. All right, number 6. So for number 6, this is real similar to if I were to have a problem like this. 2x is equal to, or no, I guess not 2x. Yeah. Actually, okay, yeah. Like something like this. 2x is equal to x or something. What I would need to do in this case, 2x squared equals x. So what I would need to do, instead of dividing out an x, I'd have to subtract an x from both sides. So 2x squared minus x equals 0. And then factor out the common factor, which is x. And then solve. Oops, 1. Sorry, that's a 2x, and that should be a 1. Jeez, come on, Mr. Cook. Okay, so this would give you 2 solutions for your answer. It'd be the same thing here. What we want to do is isolate one side, just like make it a 0 basically. So what I'm going to do is subtract away 2 cosine of x from both sides. Whatever you do, do not divide out the cosine, because if you divide out the cosine, you're going to eliminate solutions that you actually can use in this expression, and I'll show you how that works in a second, okay? So we're going to subtract 2 cosine of x from both sides. We get sine of x, cosine of x, minus 2 cosine of x, and then 2 cosine of x minus 2 cosine of x is 0. Now you look at the 2 different terms, and you notice that both of them have cosine of x's in them. So we're going to factor out a cosine of x, so we get cosine of x factored out times sine of x, that's what's left over here. And then if I factor out the cosine of x here, I get minus 2 equals 0. So from here, we've got a factored expression equal to 0. So now we can use the 0 property to solve for each individual equation. So I take each of the factors, cosine of x, and also sine of x minus 2, and I set them both equal to 0. This is very similar to a problem like this. Like if I had 2 factors, I'd set each of them equal to 0 to solve for my solution, okay? And I'm going to do the same thing here. This one already gives me a route to my solutions because I'm looking for angles that have a cosine that's equal to 0. So if you look on your unit circle, that should give you 2 different angle measurements. One of them is going to be pi over 2, so the x value is equal to 0 for pi over 2. And then also 3 pi over 2. So both of these are solutions to the equations. All right, now let's solve this one. So we need to get sine of x all by itself, just like the previous problem, just get the trigonometric equation by itself. So I'm going to add 2 to both sides, and I get sine of x is equal to 2. And this actually wouldn't give us any solutions at all because sine, its range, goes from 1 to negative 1. Because if you remember, back when you were graphing out your sine equations, or even if you look on your unit circle, the biggest value that sine can get without an amplitude shift is 1 and negative 1. Same thing here. So like if there's no amplitude out front, then it can't possibly get to 2. That's why there's no solutions from this one. So these 2 solutions that we picked up earlier, those are the only ones that actually work in this equation. So only pi over 2 and 3 pi over 2 would work here. Now let me show you why you can't divide out that cosine squared, okay? Because if you did, let's go ahead and show you like what not to do. Sine of x, cosine of x equals 2 cosine of x. If I divided out the cosine of x's from both of these, I'd eliminate a lot of the solutions. They're actually the only solutions that I've had. So it cancels out, and I get sine of x is equal to 2. And remember, sine of x cannot be equal to 2 ever. So that would actually leave no solutions. So if I cancel out the cosines, I'd only have no solutions in my answer. But as I can see, there are 2 solutions to this problem that we started off with. So yeah, just make sure that you're following the steps and not eliminating solutions that might show up a little bit later. All right, so that's it for the first page. I think that's a good place to stop this video. So yeah, and then on to the next page where we're going to be dealing with some more solving expressions.